Why can't we travel faster than the speed of light? Because c is the limit. The one restriction for space racing is that you cannot go faster than the speed of light, so let's reiterate that before we get going. The value of c, it is constant. Also, everyone is aware that attempting to attain that incredible speed would result in some bizarre events, and I'm rather certain that nobody in attendance tonight wants to be compressed into a little space. We're not to blame, it's just the way things are. Einstein's theory of relativity did a great job of describing and explaining everything, and despite the fact that it may appear counterintuitive, everyone accepts that nothing can move faster than c. Why is that? Why can't we move at the speed of light? Join me on this quest to learn more about this subject, but keep in mind that c is the limit. Light is thought to move at an infinite speed since ancient times. This seems to be supported by daily experience. When a lamp is turned on, the room is immediately flooded with light. Yet, the Danish astronomer Ole Remer postulated that light had a tremendous, but not limitless, speed as early as the 17th century. Galileo Galilei had previously tried his hand, but had failed. Galileo used a shielded lamp and an assistant to travel to the top of two hills that were a mile apart in order to conduct his experiment, which required measuring the amount of time it took for light to travel between the two lanterns. As Galileo found his lantern, the assistant on the opposite hill also found it as soon as he noticed the light. Hence, in order to determine the speed of light, the Pisan scientist would have had to calculate the amount of time required to see the light from the other hill. At that point, it would have been sufficient to divide the distance by the time. The experiment was unsuccessful because light travels a mile in about 0.000005 seconds, which is impossible to measure with the technology available to Galileo. When Romer discovered the speed of light, he wasn't seeking for it, he was just doing his job at the Paris Observatory. Instead, he was gathering considerable data on Io's orbit, the innermost of Jupiter's four large satellites that Galileo first identified in 1610. Romer aimed to calculate an exact number for the orbital period of the satellite by timing the eclipses of Io by Jupiter. These observations were important historically and practically in the 17th century. Galileo himself had proposed that charts of the satellites of Jupiter's orbital motion would serve as a sort of celestial clock. This clock may be used by navigators and mapmakers to determine the absolute time everywhere in the world, the standard time at a place of known longitude, like the Paris Observatory. They may then use the time difference to compute their longitude by finding the local solar time. After the invention of precise seagoing watches, this method of determining longitude was finally shown to be useless and abandoned. Yet, the data from the Io eclipse unexpectedly provided a solution to the speed of light, a significant scientific conundrum. We now know that Io orbits the Earth every 1.769 days. Every orbit, Jupiter completely blocks out the satellite as seen from Earth. Romer found anything strange after timing these eclipses over a long period of time. The period between subsequent eclipses decreased steadily as the Earth traveled closer to Jupiter in its orbit and increased slowly as it went farther away from the planet. These variations multiplied. Romer calculated that eclipses of Io would occur around 11 minutes earlier than projected based on the average orbital period over several years when the Earth was closest to Jupiter at E1. And the eclipses would take place around 11 minutes later than expected 6.5 months later when the Earth was furthest away from Jupiter at E2. Romer was aware that the true orbital period of Io couldn't be influenced by the distances between the Earth and Jupiter. He had the amazing realization that the limited speed of light must be the cause of the time discrepancy. In other words, when the two planets are farther apart than when they are closer to the Sun, light from the Jupiter system must travel a greater distance to reach the Earth. According to Romer, it takes light 22 minutes to travel around the Earth's orbit. The diameter of the Earth's orbit may then be divided by the time difference to determine the speed of light. The calculation for the speed of light was initially done by the Dutch scientist Christian Huygens, who arrived at the value of 131,000 miles per second. It's 186,000 miles per second, not 186,000. The discrepancy resulted from mistakes in Romer's calculation of the greatest time delay. The right value is 16.7, not 22 minutes, as well as from an inaccuracy in the orbital diameter of the Earth. The first quantitative estimate of the speed of light was provided by Romer's data, and it was accurate, which was more significant than the precise answer. In 1681, Romer left again for Denmark, where he went on to have a prominent career in both science and politics. He made extensive observations and created the most precise astronomical apparatus available at the time. He later served as the mayor and police prefect of Copenhagen before becoming the president of the state council. Of course, Romer is renowned today not for holding a prominent position in politics, but rather for being the first to measure the speed of light. We must now respond to the question of why we cannot travel at the speed of light. We need to review some of Einstein's relativity in order to respond to this question. Einstein put forth two postulates in 1905. The first is that the laws of nature apply to all inertial reference frames, or frames that move with constant speed with respect to one another and in which an item will appear to be at rest if there are no net forces acting on it. The second premise holds that the speed of light in a vacuum will be determined to be the same by an observer in any inertial reference frame. The equivalence of mass and energy, as well as length contraction and time dilation, were all derived from Einstein's theory. In particular, he understood that the so-called Lorentz factor, 1v2/c2, 1/2, where v is the relative velocity between the observer and the other train, causes an observer on a high-speed train to perceive the length of a passing high-speed train as being shortened in the direction of motion. Paradoxically, someone watching from that train will perceive the first as having been shortened by the same amount. Isn't special relativity entertaining? You can easily understand what would occur if you were to travel at the speed of light. The Lorentz factor would vanish to zero, causing your length to zero in the direction of motion. According to time dilation, a clock that is moving relative to an observer in an inertial frame of reference will be observed to tick more slowly than a clock that is at rest in that observer's frame of reference. Special relativistic time dilation is another name for this situation. The rate of time slows down when one approaches the speed of light, 299,792,458 meters per second. The faster the relative velocity, the more time will elapse between them. Although we are virtually finished, we would like to provide you with a more detailed explanation. You would likely find a ton of responses if you search the internet for why nothing can go faster than light, with many of them stating that mass would increase to infinity, which would require infinite energy to accelerate, and so on. Nevertheless, you can disregard that since the only aspect of relativity that makes sense to non-physicists is the idea of the relativistic mass increase, which is now rarely used by actual physicists due to its confusion. You can move as quickly as you like, which is the genuine response. Do you want to travel to Andromeda in an hour? It is located 2.5 million light-years distant. Try it out. You have some amazing engineering challenges to overcome, but relativity won't stand in your way. Yet along the journey, strange things will happen. 1. Light behaves in the same way regardless of your speed. It travels away from you at an exact angle of c in all directions, as if you were still. Because you are still in your frame of reference. 2. You are stationary in your frame of reference while the universe is accelerating past you. The universe becomes compacted in the direction of travel as a result of length contraction, and as a result, Andromeda is no longer 2.5 million light-years away. In fact, it's only 670 million miles, 6.8 light-hours, away, so you can go there in an hour without ever reaching the speed of light. 3. Your time seems to have slowed down for those back home. Even while you may have thought it just took an hour, to them, it took almost 2.5 million years. Once more, you have never outpaced the speed of light. As you can see, nothing ever appears to be going faster than light. It's not that something prevents you from traveling as quickly as you'd want. Rather, no matter how fast you travel, time and space change their configuration so that neither you nor anybody else, even the people back home, will ever witness anything moving faster than the speed of light. And it's unrelated to things like mass increase, needing unlimited energy, or anything else of the sort. As you can see, we live in a remarkable universe where reality frequently seems to surpass fancy. And we find it wonderful that science allows us to further expand our knowledge of the cosmos. Science will never let us down, thus all the effort we put into understanding and creating it is always well worth it. Here's where the video ends. Thank you everybody for watching. What do you think about the light speed? Are you amazed by it? Tell us in the comment section below and see you on the channel again soon.